Okay, this is section 4, chapter 1, section 4, in physics. We studied distance, velocity, and acceleration. Initially, I thought that the car would probably take off faster than the bus because it had more mass to overcome. Also, the bus has a time limit and the car doesn't, meaning the bus is on a schedule and the car isn't. We also drew graphs on the takeoff of on studying the takeoffs of a different graph. So for the first graph, it had a constant speed because it's going up. Like it started at 0 and went up towards graph, which means it was going in the same direction. Another one was that the graph started at 0 and went up, then it curved. That means that it was faster at the beginning and slowed down towards the end. The third graph I did was that it started off at 0. It was faster in the beginning and started off slow at the end. No, it was slower at the end, started off faster. No, started off slow, ended faster. I'm sorry. Next one is a graph that we did on it's almost like a seismic graph that we did on the computer. So whenever we did I think this was the car one. I think it was a voice detector. We did a voice detector and we studied all this stuff and the computer recorded it and all that stuff. So this is what I think this is what we guessed. No, this is what we got initially. This is what we got initially. This is what we got. The second went faster. It was correct. We also saw that the slope increased, so the velocity increased. Started off slow, and it ended fast. We also studied velocity versus time. The beginning and the end are flat because the car not in motion. Let me see right now. This is really retarded. Okay. Also, I learned that acceleration equals change in velocity over change in time. We did our investigation on a car, so we pushed it up a hill and then we recorded it. So I don't know if you see that. Okay, so when we first did the car, the acceleration started off slow and increased as if they were at a stoplight, and then the light turned green. He turned on to a highway. That's what I thought. The DT graph was like it starts slow, increases very fast, the acceleration. Okay. So then we recorded, recorded the initial speed we recorded the car going up the cart by taking the final speed and subtracting it by the initial speed, divided by the time. That's the final speed, subtracted by the initial speed, and getting the time right here. I learned that the steeper the slope, the faster the acceleration. The shallower, the slower the acceleration. So the steeper the slope, the faster the acceleration. The shallower the slope, the shallower the slope, the acceleration. The shallower, the slower the acceleration. Also, if it looks like this, it's going at constant velocity. Vectors have both magnitude and direction. If it's going like this, it has constant acceleration. The reason why this one has constant velocity is because it's going in one direction. The reason why this has constant acceleration is because it's increasing in speed. So velocity is direction, left, right, up, down. Constant acceleration is in speed. So it could be slowing down, or it could be speeding up. Either way, slowing down or speeding up, increasing in time or decreasing in time, is acceleration. If two automobiles have the same velocity, they do not have the same acceleration, because that does not mean that they are going at the same speed. Meaning that if you've seen two cars on the road that were going in the same direction, does it mean that they have the same acceleration? No, because each car has its own speed limit, or not speed limit, but each car has its own speed, and they're both each an individual car, basically. So if it's going in one direction, it doesn't mean it's going in the same speed. This car could be going faster than this one. Well, this one is before this car, so this one's going slower than that one. But it doesn't mean that it has the same acceleration, because the change in speed acceleration could be slow or fast. But it does have the same velocity because it's going in the same direction. Simple as that. So they're both going east, but one is going faster than the other. And that doesn't mean they have the same acceleration. We do graphs showing velocity versus time. And as you can see the velocity is going like you can't see. The velocity is direction, so it's going in not a constant direction. It's like going up, then turning, then going up some more. The time. So every time you do this, it should have the same one. See, they all have the same speed. So, yeah. Overall, in section 4, I learned the difference between velocity and acceleration. I didn't get it in the beginning, but basically all it is acceleration is the increase or decrease of its speed, whether it looks like this, or whether it looks like this, or this, or this, or this, or this. All these graphs have acceleration, all of them, each and every one of them. Now, all these have velocity too, because it's going in a certain direction. Velocity is not one direction, it's going in the same direction. Acceleration is when it's increasing or decreasing. All these guys have acceleration. So it could either be speeding up or slowing down. Either way, it's going to be acceleration. So graph A is speeding up slow, fast and faster, and accelerating upward. Speeding up slow, and accelerating upward. Graph B is moving slow, fast, then faster by moving at constant acceleration. It's going in the same direction, all going up. Acceleration. And that is that.